In this video, we see how the electron configuration of atoms and elements are responsible for the periodic or repeating trends in chemical and physical properties that we see in the periodic table. And the term used to describe these periodic trends is periodicity. You may recall earlier we were introduced to the periodic law. When elements are arranged in order of increasing atomic number, elements with similar chemical and physical properties occur at regular or periodic intervals. You'd also be familiar with a description of the periodic table, an arrangement of elements in order of increasing atomic number in which elements of similar chemical and physical properties are placed in vertical columns known as groups. And we now know the reason for these similar physical and chemical properties within groups is due to similar valence shell electron configurations within those groups. Here now we introduce the idea of periodicity, which can be described as the variation in physical and chemical properties of elements based on their position in the periodic table. And again, we know that the position of an element in the periodic table is due to its outer shell or valence shell electron configuration. The position of an element in the periodic table can be used to predict many useful trends, including atomic size, ionization energy, electron affinity, the formation and stability of ions, and therefore chemical formulas of ionic compounds, and the sizes of ions. So we'll start by looking at the trends associated with the physical property of atomic size. And roughly speaking, the size of an atom is determined by the size of the electron cloud and therefore by the size of the outermost occupied orbitals. The quantum mechanical description of atoms suggests their shape is roughly spherical, the result of the combination of overlapping orbitals in three-dimensional space. So for example, a 1s orbital overlaps with a 2s orbital, which overlaps with the three 2p orbitals, giving roughly a spherical shape, and we can therefore quantify the size of atoms in terms of the radius of a sphere. This figure here shows a plot of atomic radius versus atomic number for elements up to Z equals 86, that's radon. The dashed lines show that in general the size of atoms increases as we go down a group of the periodic table. For example, we can see that the group 1 alkali metals or the group 18 noble gases both increase in size as we go from period 1 to 2 to 3, etc. The solid lines with dots show that in general the size of atoms decreases across a horizontal period from left to right. So for example, as we go from lithium to neon, or as we go from sodium to argon in periods 2 and 3, we see that the atomic radii decrease. Another way of saying that is that atomic radii increase going from right to left across the periodic table. Now, these trends in atomic radii can be explained on the basis of nuclear charge, or more specifically the number of protons in the nucleus. For example, if we traverse across the second period of the periodic table from lithium to neon, we note that the number of protons in the nucleus increases and that the electrons are added into the same n equals 2 shell. So the increased positive nuclear charge draws the electrons within the same n equals 2 shell closer to the nucleus, resulting in decreased atomic radii from left to right. By the time we reach neon, its 10 electrons have completely filled the second shell, so that when we go to the next element in period 3, that is sodium, we note that the 11th electron needs to be placed in the n equals 3 shell, which is higher in energy and larger than any of the n equals 2 subshells. Therefore, as we go down a group in the periodic table, atomic radii tend to increase because electrons are added to shells and subshells with a higher n value and therefore a larger size. So now we can start looking at an overall representation of the periodic table and start to superimpose some general trends on this diagram. And here we can see that atomic radius increases as we go down a group and increases as we go from right to left across a period. The next property we'll consider is the chemical property called the ionization energy. And the ionization energy refers to the energy required for the formation of cations from the neutral atom by removal of electrons. Now we know that electrons within Orbitals can be promoted to higher energy levels by absorbing energy, and so, for example, electrons can be promoted from a lower energy to a higher energy if there are unoccupied levels. However, if the energy absorbed is high enough, say for example past the n equals infinity level, the electron can be ejected from the atom to form a positively charged cation, and the ease with which electrons can be removed from an atom has a significant effect on chemical behaviour. We can represent this ionisation process with a chemical equation showing that, for example, sodium can absorb energy equivalent to or greater than 495 kilojoules per mole of sodium atoms, and the uppermost 3s electron will be ejected from the atom to form the sodium plus ion plus a free electron. So this graph here shows how the ionisation energy varies with atomic number, and we can see that the general trend is that ionisation energy decreases down a group and that it increases across a period. For example, there you see from lithium going across to neon in period 2. Now the trends in ionisation energies are the reverse of the trends for atomic size, and in an inverse way both are related. The smaller the atom, the tighter the electrons are held to the nucleus and harder it is to remove them. And we know that the 1s orbital, for example, is smaller than the 2s orbital, which is smaller than the 3s orbital. And the smaller those orbitals, the harder it is to remove electrons from those atoms. As we increase atomic number across a period, we increase the number of protons in the nucleus, and therefore we increase the attractive force with which the electrons are held. It's therefore harder to remove the outermost electrons, and therefore ionisation energy increases across a period from left to right. Now the ionisation energy shown in this graph are the first ionisation energies, and the first ionisation energy, I1, is the minimum energy needed to remove the highest energy electron or the outermost electron from the neutral atom. Now electrons can be removed successively. For example, you can remove a second electron, and the energy required for that is referred to as the second ionisation energy, I2. The third ionisation energy would be the energy required to remove a third electron. Now in general, the first ionisation energy is smaller than the second ionisation energy, which is smaller than the third ionisation energy, etc. And this is because remaining electrons experience less electron-electron repulsion, and they experience a relatively greater attractive force to the nucleus, since the number of protons is now greater than the number of electrons. As a result, remaining electrons are more tightly held as successive electrons are removed. This means that removing successive electrons cost more energy. Now this table shows successive ionisation energies for the period 3 elements. And note that there is a sharp jump in ionisation energy from the first to the second ionisation energy, corresponding to the removal of an inner or core electron from sodium. So, for example, removal of the single 3s electron from the third shell of sodium only requires 495 kilojoules per mole of sodium atoms. Removal of a second electron, however, costs a lot more energy, and this because it involves removal of a core electron from the second shell, which will disrupt the stable full shell and full subshell arrangement of the n equals 2 level. And it's why the sodium ion will only ever form the 1+ ion. If we look at the ionisation data for magnesium, number 12, we see a similar pattern. Removal of the 2 electrons from the 3s subshell of magnesium costs relatively little energy. However, removal of a core third electron from the second shell, which again disrupts that stable full shell and full subshell arrangement, we see a very marked increase in energy. And so the stable ion for magnesium is therefore the 2+ ion. A similar situation exists for aluminium, where we see that removal of the 3 electrons in the third shell costs considerably less energy than the removal of the 4th core electron from the second shell. And so the stable ion for the aluminium ion is therefore the 3+ ion. And so we can see now that electron configurations can not only predict trends in the periodic table, but can also explain ionic charges for cations. The next property that we will look at is a chemical property called electron affinity. And electron affinity is the energy released when a neutral atom in the gaseous state gains an electron to form a negative ion, or in other words, to form an anion. So for example, when a chlorine atom picks up an electron to form the Cl- ion, energy is released. And this energy change, in this case, 349 kilojoules per mole, is called the electron affinity. And the fact that energy is released means that a chloride ion is more stable, and that means it has lower energy than a chlorine atom plus a free electron. And a chlorine atom can therefore said to have an affinity for electrons. Large negative electron affinity values indicate a stable anion will form. Small negative electron affinity values indicate the anion will be less stable. And so this table here shows the electron affinities for the main group elements. Broadly speaking, the general trend is towards more negative electron affinity values from left to right across a period and up a group. But there are many exceptions to this general trend. In particular, however, the non-metal groups of 16 and 17, or 6A and 7A, have the highest negative electron affinity values, which explains why they tend to form far more stable anions than metallic elements, for example. Elements in group 2 and group 18, or group 2A and group 8A, do not form stable anions at all, because placing additional electrons into their electron clouds requires these electrons to go into higher energy orbitals, and thus energy would be absorbed rather than released. So now we're able to superimpose another set of trends on our periodic table, indicating that in general electron affinity increases across a period from left to right and increases as we traverse up a group. Now, to complete the picture of general trends in the periodic table, I'm going to add two more properties to this diagram. The first refers to the metallic and non-metallic character of elements, and as we can see, elements in the upper right of the periodic table have more non-metallic character, while elements at the bottom left have more metallic character. And the last property to superimpose on this diagram is electronegativity. Now, electronegativity is actually a bonding concept, and we will deal with it in much greater detail later on. And it's actually a measure of an atom's ability to draw valence electrons to itself within a chemical bond. And as we can see here, electronegativity increases from left to right across a period and increases up a group. So this diagram here is a useful guide to being able to predict properties of elements based on these general trends and based on their position in the periodic table.